Dear students, after studying this module, you shall be able to understand simple and complex splitting patterns of various compounds, understand the first and second order spectra, understand the nomenclature of various spin systems, and also you will be able to know about the magnetically equivalent protons in aliphatic and aromatic systems. Now, let us begin this module with the study of simple splitting. In a simple spin-spin coupling, we observed that a particular proton is coupled to a set of equivalent protons and the multiplicity is decided by the total number of the similar types of protons in the molecule. This can be seen in the figure. The intensity of the peaks is according to the Pascal's triangle. Now, this is clearly shown here in the figure, the Pascal triangles and the coupling. Now, let us move our focus to complex splitting. Students, there are various factors which may lead to the complexity of the NMR spectra. If the n protons are non-equivalent, the n+1 rule is not obeyed. The chemical shifts of the coupled protons are very close, and the presence of chiral center or centers in the molecule. The presence of a chiral center makes the CH2 group distereotopic, and thus non-equivalent protons exist, which may have different coupling constants with neighboring protons. Now, you can see various cases in this figure, one with no coupled hydrogens, the other with one coupled hydrogen and the other with 3 coupled hydrogens, and their splitting patterns henceforth. Now, students, if a proton is spin coupled to 2 or more different sets of neighboring protons, that is non-equivalent protons with different J values, say Na is the number of protons of Ha type, Nb is the number of protons of Hb type, and Nc is the number of protons of Hc type, and so on. The n+1 rule does not predict the entire splitting pattern. Now, in such cases, the number of neighboring protons does not add up simply as in the first order splitting, but the multiplicity of the signal is given by Na+1, Nb+1, Nc+1 all multiplied with each other, and so on. Now, it is important to note that there may be fortuitous coincidence of some lines if a smaller J value is a factor of a larger J value. Now, this phenomenon, students, is known as complex coupling or complex splitting. Now, let us see this following compound, which is a good example of complex splitting. You can see this in the figure. Now, we have the chemical shift of Hc hydrogens is in the most downfield region, and it shows a triplet due to coupling, and its coupling constant will be JBC with 2 equivalent protons, that is Hb. Similarly, if you consider hydrogens Ha of the methyl group, they display a triplet in the upfield region, that is towards the right of the NMR spectrum due to coupling, and its coupling constant will be denoted as JAB with 2 equivalent protons HB. Now, the 2 coupling constants are not equal. The chemical shift of Hb protons is in between. One can expect a sextet for Hb, but in actual the signal of Hb appears as a quartet of triplets due to the non-equivalent nature of the coupled protons Ha and Hc, and hence it leads to unequal coupling. the signal for HB is first split into a quartet due to HA protons, and each of these 4 lines in the quartet is further split into a triplet because of the HC protons. The signal will therefore have 12 peaks in the form of quartet of triplets. Now you can see this figure clearly in this explanation with the figure given here. You can see quartet of triplets clearly displayed here with different coupling constants also. Now the appearance of the signal depends greatly on the J values. If JAB is much greater than JBC, then the signal will appear as a quartet of triplets as shown for the example above discussed. If however JBC is much greater than JAB, then the signal will appear as a triplet of quartets. Now students, in most cases the J value are not much different, and we will observe neither a clean quartet of triplets nor a clean triplet of quartets. Many of the peaks overlap, producing a multiplet, and it is difficult to extract the J values from this. Now similarly, the splitting pattern, that is which is of second order splitting for the methyl acrylate, can be explained. Now you can see a multiplet in this figure, and we are going to explain the second order splitting for methyl acrylate using this figure. The proton HC in methyl acrylate has 2 different types of neighboring protons, HA and HB, and hence it couples to both HA and HB, but with 2 different coupling constants. HC is trans to HA across the double bond and splits the HC signal into a doublet with a coupling constant of 3 JAC is equal to 17.4 Hertz. Now in addition, each of these lines in doublet is further split by HB geminal coupling into 2 more doublets, each with a small coupling constant of 2 JBC is equal to 1.5 Hertz. This type of pattern is referred to as doublet of doublets, also abbreviated as DD. Now you can see a doublet of doublets and its J value here in this figure. Similarly students, the signal for HB at 5.64 ppm is split into a doublet by HA with a coupling constant 3 JAB is equal to 10.4 Hertz, which corresponds to the cis coupling. Now each of the resulting lines is split again by HC with the same geminal coupling constant 2 JBC is equal to 1.5 Hertz. The overall result is again a doublet of doublets. Now the signal for HA, which is at 5.95 ppm, is also a doublet of doublets with coupling constant 3 JAC is equal to 17.4 Hertz, which arises due to trans coupling, and 3 JAB is equal to 10.5 Hertz, which arises due to cis coupling. Now I want you to note something here students. The signal shown above looks like a quartet, but it is not a quartet, because in a quartet the line intensities are 1:3:3:1, and the individual peaks are equally spaced. In a doublet of doublets, all the lines are of equal intensity and the individual peaks are not necessarily equally spaced. Hence, for complete identification of the splitting pattern, we must look carefully at the number of lines, their shape and their intensity. Now, in some cases JAB and JAC will be almost identical. Now, let us consider an example for this, which is the proton NMR spectrum of 1-nitropropane, that is a 3 carbon and having a nitro group. Look carefully at the splitting pattern of the HB protons. Having a delta value of approximately 2 ppm, the signal looks like a sextet because the two coupling constants JAB and JBC are very similar. In such a case, students, it appears as if there are 5 equivalent neighbors, even though all 5 protons are not equivalent. Due to the very close value of both the coupling constants, several lines coincide to give a deceptively simple multiplet, that is a sextet. One, however, may expect 12 peaks at high resolution. Similarly, considering the case of 1-bromo-3-chloropropane, the CH2Cl and CH2Br protons are not chemically equivalent. In spite of this, the middle CH2 appears as a quintet. This again is due to the fact that the magnitude of coupling to both type of protons is very similar. Therefore, it seems to obey the n+1 rule. First order spectra. If the splitting pattern of a multiplet is given by the n+1 rule, then the spectra is called as ideal or first order spectra. This is usually observed if the spin coupled nuclei have very different chemical shifts, that is delta nu is large as compared to the J value. The chemical shift value and the coupling constant J can be measured directly from the spectrum. Now students, the first order spectra can be analyzed by the features. Number 1, the multiplicity of the peak is given by the expression 2Ni plus 1, where I, as you already know, is the nuclear spin of the concerned nucleus and N is the total number of coupled nuclei. The relative intensity of the component peaks of a multiplet is given by the coefficients of the terms in the binomial expansion of x plus 1 raised to the power n for the nuclei with I is equal to 1 by 2. Now, the center of the multiplet gives the chemical shift of the concerned nucleus. The last and the fourth point, students, is that the separations of peaks in two coupled multiplets are exactly equal and correspond to the coupling constant. Now, it is well known that the chemical shift measured in Hertz depends on the applied magnetic field, and the value of delta nu increases as the field strength increases. The value of coupling constant J remains constant, and hence the value of delta nu divided by J will increase on increasing the field strength. Therefore, at high field strength, most proton NMR spectra become first order. It is important here, students, to notice that high field NMR instruments give better resolution and relatively easily interpretable spectra. Now, let us shift our focus to the second order spectra. If the coupled nuclei have approximately same chemical shifts and their chemical shift difference is comparable to the coupling constant between them, the first order splitting rule, that is 2Ni plus 1, is not applicable. The splitting pattern in a multiplet is distorted and the bands are no longer symmetrical. In fact, signal splitting disappears if the chemical shifts of the coupled nuclei are the same. Such types of spectra are known as second order spectra. Now, it is difficult to measure the chemical shift and the coupling constant values simply by just analyzing the spectra. Now, as the value of delta nu divided by J decreases, the coupled multiplets approach each other and the inner lines increase in intensity and the outer peaks decrease. In some extreme cases, the outer lines may too become weak to be observed and hence the resulting multiplet is wrongly interpreted. Since students, there is leaning of coupled multiplets towards one another and hence the chemical shift values cannot be given by the center of the multiplet which is observed. In such cases, the chemical shift is given by the center of gravity. The chemical shift values can be calculated by the mathematical formula, like delta nu AB is equal to square root of brackets nu1 minus nu4 multiplied by brackets nu2 minus nu3 bracket closed. Now, in this case, delta A will be equal to nu1 minus brackets nu1 minus nu4 bracket closed minus delta nu AB divided by 2. Thus, delta B here will be delta nu AB minus delta A. Now, let us learn how the nomenclature of the spin system is done. A scientist named Pople developed a convenient method to designate the type of spin coupled systems. Each chemically different type of proton is assigned a letter of the alphabet like A, B, C and so on. Protons which have chemical shifts nearly same are assigned the letters that are close to one another, that is A, B and C. If the chemical shifts are widely different, then the letters which are far apart from one another are assigned for these protons. Now, for example, ABC versus XYZ. If the groups of nuclei are magnetically equivalent, they are labeled as AN, BN, ANBN, etc. For example, CH3 group represents an A3 system. The magnetically equivalent protons have same chemical shift and hence group of one particular magnetically equivalent protons AN couple equally with another group of magnetically equivalent protons BN. If protons are same chemical shift but magnetically equivalent, they are labeled as AA dash system. Thus, in systems such as A2B2, A2X2, the A type protons have identical coupling with the B type protons. But in the case of AA dash, XX dash, the system with the coupling constants are not same, that is JAX is not equal to JAX dash. If three types of protons are involved and they have almost the same chemical shifts, the system is assigned as ABC system. Whereas protons having widely different chemical shift, the letter M, letter from the middle of the alphabet case, is used to designate this system, that is AMX system. In general, a system in which protons have very different chemical shifts display first order spectra, whereas protons having almost similar chemical shifts display a second order spectra. Now, the different type of spin systems are described in detail. First, we would like to consider the two spin systems, that is of the type A2, AB, AX. Let us come on to the A2 system, students. A system having two equivalent nuclei is designated as A2 system. This system always shows a singlet. The methylene protons in an aliphatic chain with no protons on the adjacent carbon atoms constitute an A2 system. For example, a compound like 1122 tetrachloroethane is a good example of the A2 system. Let us now shift our focus to the AB system, which is also an example of two spin system again. A system containing two protons, say HA and HB, which couple with each other but do not couple with any other proton, and their chemical shift is delta A minus delta B. Values difference is comparable to the coupling constant JAB. In AB type system, students, both the nuclei are strongly coupled and are designated by adjacent letters AB in the alphabet case. In such systems, the doublets are distorted, that is, they are not 1:1 in their intensities. The inner lines become larger and the outer lines become smaller. Now, let us consider AX type system. A system having two protons, say HA and HB, with their chemical shift difference values delta A minus delta B much larger to the coupling constant JAB. Now, this system shows two distinct doublets with all the four lines of equal intensity. Now, the example of AX system, students, is dichloroacetaldehyde, or with the formula Cl2CHCHO. Now, you can consider here the various two spin systems, one in this figure, that is first one is AX, the second one is AB, the third one is A2 system. Now, let us move to the three spin systems like A3, AB2, A2B, AX2, A2X, ABC, AMX and ABX. First of all, we will consider the A3 system. A3 system contains three equivalent nuclei and always shows a singlet in NMR spectra. Examples are CH3I, that is methyl iodide, and Cl3CHCH3, that is trichloroethane, and CH3COOCH3, that is methyl acetate. Two A3 systems at different chemical shifts. Second one is AX2 and A2X systems. In this system, two magnetically equivalent protons are coupled to the third proton, which has a chemical shift value widely different from the other two protons. For such a system, NMR spectrum shows a proper doublet with the intensity 1:1 and a triplet with the intensity of 1:2:1. The examples are Cl2CH CH2Cl and Cl2CH CHCl CHCl2. That is, first is the chloro and the dichloro in the ethane, and the third one is the propane system with dichloro, 2 chlorine atoms at both the ends and 1 chlorine in the central CH. Next comes the AB2 and the A2B systems. In this system, students, two magnetically equivalent protons are coupled to the third proton, which has a comparable chemical shift value to the other two protons. As the ratio of the chemical shift values, difference to coupling constant is very small, each line of the doublet is further split into 2 and also the center line of the triplet splits into 2 and thus producing total 8 lines in the spectrum. In addition, the simultaneous change of spin states of all 3 protons produces a weak signal which is observed only when delta nu by J is very small. Thus, a total of 9 lines are possible in an AB2 or A to B system. Now, the actual appearance of the spectrum depends upon the ratio of the chemical shift to the coupling constant, that is delta nu divided by J. Now, examples of the AB2 or the A to B systems are 2,5-dichloronitrobenzene, 2,6-dichloropyridine and pyragalol, etc. Let us come to the study of AMX type of systems now. In AMX system, students, 3 non-equivalent protons are present with large value of delta nu by J ratio. Many vinyl systems such as CH2 double bond CHY display AMX system, that is where Y is a strongly electronegative substituent. There are 3 coupling constants for such systems. The trans coupling JMX is larger than the cis coupling JAX. JAM is the geminal coupling with a significant value. The AMX system exhibits 12 lines of almost equal intensity. The coupling constants can easily be obtained from the analysis of the spectrum. The peaks due to the protons HA and HM are split into doublet by coupling with HX proton. Now, each line is further split into narrow doublets. The doublet of HA will split by HM and similarly the doublet of HM will be split by HA, having small allylic coupling JAM. Similarly, students, the hydrogen HX is split into a doublet by coupling with the proton HM and then each line is further split into doublets with the proton HA. Now, this all coupling can be explained clearly by this figure as you can see here, and the ABC system is also shown in this figure. Now, ABX system. In ABX system, the chemical shift difference and the coupling constant between 2 of the 3 interacting nuclei are of comparable magnitude and both are coupled to the 3rd nucleus, which has chemical shift very different from both the nuclei. Now, examples are parachlorostyrene and styrene. Now, let us consider styrene as shown in the figure. In styrene, all the 3 vinylic protons are non-equivalent and hence have different chemical shift, giving rise to 3 separate signals. The coupling constant between any 2 of the protons, that is JAB, is approximately equal to 2 Hertz, JAX is equal to 11 Hertz, JBX is equal to 18 Hertz, are different as I have told you. The chemical shift for protons HA and HB are nearly the same, but the hydrogen HX has a very different chemical shift, that is more downfield from HA and HB due to the anisotropy effect of the benzene ring, and we have discussed the anisotropy effect in much detail in the previous modules. Each of the 3 signals is split into 4 lines, that is a doublet of doublets. The peak of HX is split into a doublet by HB, and again each line is split into a doublet by HA. Thus, a total of 12 peaks must be observed. Now, since the value of JAB is very small, which leads to the overlapping of closely spaced signals observed for HA and HB, resulting into total 4 lines instead of 8 lines due to HA and HB. Now, let us discuss the ABC system. In an ABC system, the chemical shift differences among the 3 non-equivalent protons are not large in comparison to the corresponding coupling constant. The spectrum of such system is complex and exhibit a total of 15 lines. The values of coupling constants for such systems can only be calculated using computer simulation methods. Manual analysis will lead to approximate values of coupling constants, which in severe cases can be drastically wrong. The vinyl system can give ABC system if the electronegativity of the substituent is not much higher. Example of the ABC system can be allyl bromide as shown here to you in the figure. In an ABC system, the chemical shifts of all the 3 protons are not much different. The coupling among the protons HA, HB and HC and also CH2, the allylic coupling is very less in magnitude and gives a very complex spectrum. Now, 3 multiplets due to HA, HB and HC merge into one another. The methylene protons can appear as a doublet due to coupling with HX. However, sometimes further splitting in this doublet may be observed due to small allylic coupling with protons HA and HB. Now, note here students, as we know that the order of a spectrum is partially depending on the sensitivity of the instrument, at 60 MHz NMR instruments, the vinylic system of styrene can show the pattern of an ABX system, while the system may become the first order AMX system at 300 MHz instrument. This is due to the fact that the ratio of delta nu by J depends on the field strength and it increases as the field strength also increases. Now, let us discuss about magnetically equivalent protons. Now, protons which have the same chemical shift as well as have the same coupling constants with the same partner nuclei in the molecule can be called as magnetically equivalent protons. The homotopic and enantiotopic protons are chemically equivalent, but they will not necessarily be magnetically equivalent also. They may be or may not be magnetically equivalent. Thus, all the magnetically equivalent protons are chemically equivalent, but vice versa is not true. In the Pople nomenclature, such magnetically inequivalent nuclei are given an AA- designation. Such kinds of system do not give first order splitting patterns. Now, let us take a few examples to understand the concept of magnetic equivalence. In the first structure in this figure that you can see, there are 2 types of protons, that is tribromobenzene. The 2 HA protons have same chemical shift due to the plane of symmetry, whereas HB has different chemical shift. Both chemically equivalent protons HA are showing coupling with the same proton, that is HB, and with no other proton. Hence, they are magnetically equivalent. However, if you look at the second structure in which you can see just bromobenzene, protons HA and HA dash as well as HB and HB dash are chemically equivalent. That means they have a plane of symmetry. The HA proton has a J3 coupling constant to the HB proton, whereas the J5 coupling to the HB dash proton. Thus, the proton HA has different coupling constants to the two chemically equivalent protons, that is HB and HB dash. Hence, both HA and HA dash protons are not magnetically equivalent. Similarly, students, HB and HB dash are not magnetically equivalent. The magnetic equivalency can be seen in different aromatic systems which are described. First, let us consider in this the ortho disubstituted benzenes. The magnetic inequivalence phenomenon can be seen in ortho disubstituted compounds when both the substituents are the same, such as orthoxylene, 1,2-dichlorobenzene, 1,2-diaminobenzene. Now, it is clear, students, that the both HA protons and the both HB protons are chemically equivalent due to the presence of the plane of symmetry bisecting 1, 2 and 4, 5 CC bonds. One can expect a doublet of doublets for each signal. Let us talk about either proton HA. The HA proton at C3 has a J3 coupling to the nearest HB proton, that is proton at the C4 position, and a J4 coupling to the other HB proton, that is the proton at C5 position. Thus, the proton being observed as different coupling constants due to the two chemically equivalent protons, that is HB. Hence, both HA protons are not magnetically equivalent. Similarly, both the HB protons are chemically equivalent but magnetically inequivalent due to their different coupling relationships with both HA protons. Para-disubstituted benzenes. In 1,4 hetero-disubstituted benzenes, there is a plane of symmetry passing through the C1 and C4. Hence, both HA protons and both HB protons are chemically equivalent. Now, students, let us first talk about the proton HA. The HA proton at C3 position has a J3 coupling to the nearest HB proton, C2 position, and a J5 coupling to the HB dash proton, that is a proton at C6 position. Thus, the proton being observed has different coupling constants to the two different chemically equivalent protons, that is HB and HB dash. Hence, both HA protons are not magnetically equivalent. That is why designated as HA and HA dash. Similarly, both the HB protons are chemically equivalent but magnetically inequivalent. That is why designated as HB and HB dash due to their different coupling relationships with both HA protons. Now, this can be seen here in this figure clearly. Now, let us consider other aromatic systems: pyridine, 4 substituted pyridines, N-substituted or unsubstituted pyrrole, and other aromatic heterocycles such as phosphols, furon, thiophene, etc. all have the same symmetry framework as para-disubstituted or ortho-homo-disubstituted benzenes and will present as chemically equivalent but magnetically inequivalent pairs of protons. It is important to note that in heterocycles, generally 3J coupling values can be significantly smaller in benzenes and the manifestation of magnetic inequivalence may be subtle. Now, it can be seen here in the figures as I have mentioned in the names of the structures before. Consider the 3 isomeric structures of difluoroethane. All the 3 isomers display an example of chemical shift equivalent, but which are not magnetically equivalent. Now, you can see here clearly in this figure all the 3 structures or the 3 isomeric structures. Now, students, it is clear from the symmetry that the 2 protons as well as the 2 fluorine atoms are chemically equivalent, but due to the fixed stereochemistry of the molecule, that is restricted rotation about the double bond, as you can see here, the protons and the fluorine atoms are magnetically inequivalent. There are 3 different couplings for each proton. For HA, the coupling constants are JHAFA, JHAFB and JHAHB, whereas for HB, coupling constants are JHBFA, JHBFB and JHBHA, and JHAFA is not equal to the coupling between JHAFB. Similarly, students, JHBFA is not equal to the coupling constant JHBFB. Now, students, let us summarize this module. The intensity of the peaks in case of simple splitting is according to the Pascal's triangle. Various factors like non-equivalent protons, close chemical shifts of coupled protons and presence of chiral center in a molecule leads to the complexity in an NMR spectra. At high field strength, most proton spectra become first order. It is important to notice that high field NMR instruments give better resolution and relatively easily interpretable spectra. Signal splitting disappears if the chemical shifts of the coupled nuclei are the same. Such type of spectra are known as second order spectra. Various spin systems have been differentiated and named by Pople, and their spectra has been discussed in this module. All magnetically equivalent protons are chemically equivalent, but vice versa is not true. Now, after having finished this module here, students, I hope you found it very informative regarding the first order and the second order spectra.